Okay, so I will talk, my title is A Possible Explanation of the Atmospheric Kinetic and Potential Energy Spectra. And my co-workers are my graduate students, Enrico Di, and my former graduate student, Andreas Valdi. So this is the problem I have been working with for many years now. Well, I've been working with other problems as well, but I started about 15 years ago to work on this problem. And this is the kinetic and potential energy spectra of the atmosphere, measured by commercial aircraft. Here's the different wind components. This is the meridional wind, this is the zonal wind, and this is the potential energy spectrum measured by temperature, where potential energy here refers to the restoring Archimedes force of a fluid particle. And these two are shifted one and two decades here to the right, these spectra. And here we see a short, maybe k to the -3 range here at wavelengths from 2,000 kilometers down to 500 kilometers. And here we see the k to the -5/3 range here at wave numbers from wavelengths from 500 kilometers down to kilometer scales. Yes. And the question is, how can we get such a spectrum? I read in Uriel Frisch's book, actually, he said something that it's paradoxical that we find the k-3 spectrum here at larger scales, k to the -5/3 at smaller scales. Because if this had been two-dimensional turbulence or something like that, it would be the reverse, as you know. And the question is here, is this something like a 2D turbulence cascade, inverse cascade, or is it like a 3D forward energy cascade here? And this range here, is this like a 2D turbulence entropy cascade or something like that? And today I will hopefully give you the answer. And the answer will be quite simple and dull, but I think it's the correct answer. As many, you will probably, hopefully you will say we knew that all the time. So first I will give you a brief presentation of what is called quasi-eustrophic turbulence. Quasi-eustrophic turbulence is very much like 2D turbulence. It was the theory of quasi-eustrophic turbulence was developed by Charney, but it was mapped onto the theory of the two-dimensional turbulence by Kreisler. But here, the important quantity is potential vorticity. It's the ordinary vorticity, but there is one extra term here, which depends on the buoyancy here. I have dimensionalized buoyancy, so it has the same dimension as velocity here. F is the Coriolis parameter, N is the Brunt-Väisly frequency. And just as two-dimensional turbulence, it has two quadratic invariants, potential entropy and total energy, here where energy is kinetic energy plus potential energy. And this is the traditional picture of two-dimensional turbulence, which you all are familiar with. And the same applies for QB turbulence. But the new quantity here is the potential entropy here instead of entropy. So it's just like two-dimensional turbulence, but it's not two-dimensional. It's a three-dimensional type of flow, but it has two quadratic invariants, just as two-dimensional turbulence. So can this be applied to the atmosphere? Well, this is the question. And how can it be applied? Lilly suggested that there are two energy sources here. The traditional known energy source at 1,000 kilometers or several thousand kilometer scales out here, which is baroclinic instability. And then one more peculiar unknown energy source here. And energy would then cascade in upscale here, and entropy would cascade downscale here, and this would generate such a spectrum. And this is actually possible to, such a spectrum is actually possible to generate also in a two-dimensional system by two energy sources. But the problem is that the Rossby number, which has to be small, it's a measure of the strength of the rotation. So the Rossby number, if small, we have a very strong rotation, and then we have an inverse energy cascade. But the Rossby number here is order unity or even larger, so it's very hard to apply this type of theory to this range. So Lilly suggested that it was only the effect of stratification that made the energy go upscale. But subsequently, it has been shown by myself and others that if you only have strong stratification and not strong rotation, you actually get a forward cascade. So this is implausible. This is a recent proposal by Tulloch and Smith. They have published this in several papers. They suggested that this should be a surface effect. We are close to the top of Smith. No, not Leslie, Schaffer-Smith. Okay. It should be a surface effect due to the fact that the aircraft are flying close to the tropopause. But he showed that the surface effect also generates such a spectrum. But the problem is that this spectrum has also been measured in the middle of the atmosphere, so it cannot be a true explanation. This was another explanation proposed by Tung and Orlando, that you only need one energy source here. This like 2003 or 5 or something like that. But it was well, they proposed that this type of spectrum could be explained within the quasi-eustrophic model. But the quasi-eustrophic model would generate a kind of weak, hidden, and forward energy cascade from the large-scale source. But and they also gave some numerical evidence in support of this. But I believe that the numerical evidence is just, well, it's just bad resolution. So, and many other people believe that too. So. But nevertheless, the idea is quite interesting, I think. I was very negative to this idea, and I thought, and looking at the simulations, I was even more, after having looked at the simulations, I was even more negative. But now, I have picked up some element of this idea, nevertheless. So, now I come to our explanation. We start with a so-called primitive equation system. It's the same, essentially it's the same Boussinesque approximation, but we make another approximation also. We suppose hydrostatic balance here also. Not only in the background field, but also in the turbulent field. And this has been used to simulate weather for decades, this system. And we reformulate this system in terms of potential vorticity, the Charney potential vorticity, and two adiostrophic components here, which are small in the limit of strong rotation, strong stratification. And then we apply the Charney scaling here. So A1 and A2 are small in the Rossby number, and the vertical coordinate is kind of stretched. The vertical coordinate we use is kind of stretched by a factor of f over n. And then we write up the equations. And the equations, well, they are quite complicated. But
actually, I haven't quite understood. Can you move to the previous slide? I mean, there are some of the, no, the one with the scaling.
Yeah.
That's the next one. Yeah, all right, this one. What is small and what is large? What is order 1 and so on? I mean, I don't see
the Rossby number, as we will see, is small. Okay. F over n is small. So So this is just, we scale the equations in this way.
Yeah, but there is a hidden epsilon. I would like to see where it is, what is epsilon squared, what is 1 over epsilon, and so on. I mean,
no, well, this is the, no, we are not making an epsilon here. We just scale the equations in this way, okay?
You're not throwing out anything so far.
No, we are not throwing out anything. We just
no problem.
Scale it in this way.
You are making this discarding noises. This is why.
Yeah. Okay.
But I understand.
Okay. So, and this is the same set of equations, but
Nothing
scale.
missing.
Okay. Okay. Nothing missing. And the only parameter here we have actually. We have added some viscous parameters here, enabled to simulate them and in order to get dissipation and so. But the only other parameter which we have here is the Rossby number actually. So we have no Frode number. The Frode number is implicitly set to 0 by the assumption of hydrostatic balance actually. And if we put now the Rossby number to 0, we retain the Chorny model. Okay. So then we get two balance equations here, and we get Chorny's equation here. But the assumption here is that we have a small but finite Rossby. And if we have a small but finite Rossby number, we have to leading order. We have kind of two-dimensional dynamics. We have a forward entropy cascade, but we have a weak. Just as you had, we have also a weak forward energy cascade. And the strength of the forward energy cascade depends on the Rossby number. So it's an extremely simple hypothesis. Because we don't have perfect entropy conservation here. We only have perfect entropy conservation when the Rossby number is small. So if we take a small but finite Rossby number, most of the energy will go upscale, but some of the energy will go downscale, and this ratio depends on the Rossby number. So it's an extremely simple hypothesis. So it's not like a phase transition or something. It's just as you saw, it's a gradual change from one type of dynamics to another type of dynamics. And the important parameter deciding how much of the energy which is going downscale and how much is going upscale is the Rossby number. Okay. So it's an extremely simple hypothesis. So in the limit, just as I said, in the limit of 0 Rossby number, the Chorny equation is retained, and we have a perfect inverse energy cascade. So, but what happens then when Rossby number is small but finite? Well, we still have, to leading order, a forward entropy cascade from the forcing wave. Okay? And if we put in entropy at the rate eta here, we can relate at a particular forcing wave number. We can also know the energy injection rate P here. And of the injected energy, some of the energy which is injected will go into a hidden forward energy cascade, which is kind of weak, but is not seen until it shows up at a particular wave number. So I just make the assumption here that epsilon here, which is the amount of energy which is going downscale, it's P times Rossby number times power n. First I came up with some rather nice theoretical results that showed that this should be 2, and then I changed my mind and said maybe it's 1. I got some equally nice theoretical argument showing that it was 1, but then I said, well, let's try and see what happens in the simulation.
Sorry.
Yeah.
In your simulation, you have both hyperviscosity and friction.
Yeah. Yeah. So we have kind of Ekman friction and hyperviscosity.
Is P the total injection rate?
P is the total So now we simulate this system in a cubic box, but remember that the vertical coordinate is stretched here. So it's only cubic in so-called in the Charney space. Okay. So in real life, n over f in the atmosphere is order 100. So we would have an aspect ratio of 1 to 100 because we have stretched it, the box. Okay. And well, in the simulations, I will show you later, but well, if we just assume that we have an energy spectrum which is just a linear superposition of these two, we get the transition wave number here from k to the minus b to k to the minus 5/3.
I don't understand why are you adding them up? I mean, they're
Well, it's just a
regional k-space, or am I mistaken?
well, you can argue. It's just a guess. Okay. Okay. And we say that the forward energy cascade will generate this spectrum, and the forward anisotropy cascade will generate such a spectrum, and where will they meet? Okay, it's extremely. You can argue, maybe develop some more refined argument developed on the time scales, that they will not.
Probably don't
they will
really
not
need the addition. You just assume it's one in one.
Yeah.
And then you stop out.
Yeah, and then I say, where will I get the transition scale? Okay, and the transition scale will scale with a Rossby number to the power of minus n to 2 here. Okay, so if the Rossby number goes to 0, the transition scale will move to very large scale. Okay.
Eric, would it be reasonable to assume that the transition scale will happen where local Rossby number is 1?
No, there's no. It's not a local Rossby number, because the local Rossby number.
I'm not talking about this.
The local Rossby number of this cascade is always the same. It's not dependent on the k. That's the problem here. So that this Rossby number, it's the so-called. It's the Rossby number based on this times you get here, and it's one global Rossby number. Okay, and you have one governing instability or force, which is in the atmosphere would be baroclinic instability, and this Rossby number decides how much is going downscale and how much is going upscale. So it's not the local Rossby. Okay, this is about it's 1,000 simulations, standard simulations, okay. And here are some results here. Here we have varied the Rossby number, and here is the total spectral energy flux, and with increasing Rossby number. This is a quasi-eustrophic simulation, so here we have less than...
I didn't catch it.
It's
the resolution. What is the resolution of these?
What 1,000 cube? Cube in the in the Charney, in the stretch. Yeah. So here we have a quasi-eustrophic simulation, and here less than 1,000 of the energy is going downscale. Okay. So there is essentially no forward energy cascade. And here we increase the Rossby number. So here the Rossby number is like still very small, it's 0.02 or something like that. And here's the largest Rossby number, which is 0.2. And in the atmosphere we would maybe be here 0.1. So here at the largest Rossby number, nearly 1/2 of the energy is actually going downscale. And as we decrease the Rossby number, less and less energy is going downscale. And here's the quasi-eustrophic simulation, and we have k to the minus 3 here, as predicted by Charney. And then we increase the Rossby number, and we get a transition here, which moves towards smaller k as we increase the Rossby number. Okay. So it's according to this idea, this very simple idea. We can generate such a spectrum only from one energy
The DD
source.
spectra are angular average over all three directions.
Yeah, this is actually the horizontal spectrum.
Ah, that's the horizontal.
Yeah.
Oh,
But we would get similar spectra, but in the vertical it's a little bit
Yeah.
more tricky. So the dependence here of the amount of energy going downscale with Rossby number, it turned out to be neither 1 Rossby number to the power of 1 or nor 2, as I suggested. I had 2 different arguments, but to the power of 3/2, and I can't explain that actually. But nevertheless, it's a confirmation of the idea that the Rossby number is the determining parameter, how much energy is going downscale and how much is going upscale somehow. And I can't guarantee that this is a general.
You study the vertical structure of things varying around.
Yeah.
Quickly the third direction, or
Yeah,
can you
yeah.
make some approximation that would reduce the numerics to being two-dimensional?
No, I don't think so.
A clever approximation.
No, well, you have to be more clever than I am, maybe. So this is some flow field. I think it's the potential vorticity here. And as you see here at Rossby number 0, we have very large vortices here dominating. I want to emphasize again that the box is now cubic in the, not in the real space, but it's stretched by a factor of n over f here. So if we would translate this to a real atmospheric flow, the aspect ratio would be maybe 1 over 100 here.
But what about the small?
And here is the
small
large.
scales, are they? Is there considerable three-dimensionality in the small scales?
Yeah, yeah, yeah. It's a forward cascade dynamics. It's
But
of course
you
extremely.
have some evidence that it becomes roughly isotropic when you're well into this K minus 5/3 regime.
No, it's not isotropic. No,
No, I mean, is it extremely anisotropic?
extremely anisotropic. Remember now that the box is stretched here by a factor of n over f, and the equations we have developed is the equations when we take f over n equal to 0. Okay, we go in this limit. So it's extremely anisotropic. Also in this, and you can also, I mean, it has to be, what scales are those in the real atmosphere? It's 500 kilometers. The height of the atmosphere is 10.
Suppose you extrapolate to what you would be able to see if you had a computer a million times faster at an extremely high K, would it become isotropic, or what's your guess?
At the Usmidov length scale, which is about 10 meters, then you would go into the regime of isotropic zone. 10 or maybe 20 or 30 meters or something. Okay. But this would be translated to.
Still compatible with the equation that you're using.
Well, for larger scales than the Usmidov length scale, yes, but not for smaller scales. Okay.
Do you have waves?
Yeah. Can I feel a little bit.
Yes. So if I'm not constrained by what he said, you have 5 minutes.
Okay. Okay. So I will finish up and then we take the questions. Okay. It's
sure.
So we have also studied third order structure functions, because when I started to do this, my first idea was to calculate the third order structure functions from aircraft data and then decide the direction of the cascade. So this was the first thing I did 10 years ago. And here there are different predictions here, as you all know, we studied the kind of longitudinal plus longitudinal transverse third order structure function, because this is a more relevant energy measure than only one of them. And we see a change of at small r here, corresponding to large K, we have a negative, fairly, well, linear range here for the Rossby number. But then we have a change of sign, and we have the cubic relation here, which is characteristic for 2D or Foster-Stokes dynamics. We can compare this with the measurement from the stratosphere. I did this together with John Chu at MIT. Actually, I did it wrongly the first time I did it, but then he repeated it and wrote to me, I have repeated it now, and I got not exactly the same result as you did. And it turned out that it was a bug in my program. I'm not very proud of that, but I have to say it if you have read my first paper. But I'm proud of saying it, actually, of admitting it now, because it was a long time ago. And we got in the stratosphere, we got a linear negative range here in the mesoscale range, clearly indicating a forward cascade dynamics. And then we got a change of sign here at approximately 300 or 400 kilometers here. And then we got maybe a small, tiny cubic range here, which could be a sign of a forward entropy cascade. And we get something similar in our simulations here, where now here, this transition scale is moving with the Rossby number, which is the parameter which is important here. Okay, so we have performed high resolution numerical simulations of the primitive equations. And energy is found to cascade more and more towards smaller scales as Rossby number is increased, challenging the spectra to k to the minus 5/3. And the structure functions are in agreement with theoretical arguments and as well as observations in the atmosphere. Thank you very much.
Any questions? Yes.
Did you say it's isotropic at small scales?
No, not really. You can apply isotropy. It's heavily scaled, and isotropy is taken care of with this.
Remains unassociated.
Yeah.
Normally, if it wasn't for this unpleasant, and I got unpleasant from some point of view, in order to throw more light on what proper scaling is, this n value, I will try some closure on this and try to derive it by hand.
Yeah.
But that's really painful in the isotropic case.
It's complicated.
Yeah, we should look at the equation and see if there is some weird two-dimensional, yet another quasi-two-dimensional approximation that can be made. But it may be tough. The other question? Yes, okay.
Okay, so 2 questions. Is there any role of waves there?
We see waves. The way we force it here we force in the potential vorticity equation, but nevertheless, the forcing is white noise, and it will generate waves at around the forcing scale. But clear waves, we have also studied frequency spectra waves. So as the cascade goes on, those peaks in the frequency spectra, they broaden and broaden more and more. So we see the time scale of the wave, but we don't see any
Identity.
yeah, we don't see any sharp.
Yeah. Then the
peaks.
second question, which actually related, right? So you start with Rossby number much less than 1,
Yeah.
which indicates waves if you were 3-dimensional. Okay, and then you said, okay, local Rossby number is constant, but it's not actually, it's logarithmic, right? So as you go along the k-3 direct entropy cascade, your vorticity grows logarithmically. Okay, so you actually at some point you will reach local Rossby number which is big. So I wonder.
I don't think that this is the. I don't think this is relevant.
Look, Rossby number, local Rossby number is a measure of nonlinearity.
Yeah.
And so if you have small local Rossby number, you have weakly nonlinear waves with sharp peaks. You said you don't see them, and that's an indication of what I said.
Well, to be honest with you, Sergey, I have been working with this idea of local Rossby number for many years, and when I gave up that idea, I made progress. So, so it was only an obstacle because if you make order of magnitudes estimates of what you're saying, it doesn't make and take the order of magnitudes in the atmosphere and real cases, and it doesn't make sense. So I gave up that idea, but it was hard to do it. But I think you should do it too.
Okay. Low-level question. I mean, what happens to your simulations if you don't use hyperviscosity, just use conventional viscosity?
Well, you will have essentially the same type of dynamics, but you don't have such clean inertial ranges. You will have viscosity is influential at higher wave numbers than what is seen here.
So even with 1024 cubed, you will not be able to see enough scale with conventional viscosity.
But there is no point in using conventional viscosity here because remember that we have stretched the vertical coordinate here by a factor of n over n. So the real viscosity we use here is really extremely anisotropic if we would scale it back. So you see what I mean?
No,
so there is no we
Okay.
can't reach that. I mean we cut off at maybe 10 translated to the atmosphere. Our cutoff is maybe at 10 kilometers. So
Okay, good. So perhaps now we should break for coffee.